now that we know that electrically charged objects are going to interact, they're going to attract or repel, what we're going to look at is what is the size of that force that's actually doing the attraction or doing the repelling, and how can we understand how to quantify that value, okay? So we're going to look at the electric force, which we classify as something called Coulomb's law, right? And really this is the force that's acting on any two charged objects. And obviously if you have more than just two charged objects, we're going to look at how those interactions are going to be. But any two charged objects are going to follow the fundamentals of Coulomb's law, okay? And so the relationships that we find is that the force that is acting on a charged object is going to be proportional. So this doesn't mean equals, but it's proportional to charge 1 multiplied by charge 2, so the product of those two values, okay? We also find that the force is proportional to 1 over r squared. It's an inverse square law, right? So this is pretty important. The inverse square law basically showing that as things get farther apart, the size of that force is going to drop drastically, okay? And we're going to put those together to have our equation, which is the electrostatic force, or Coulomb's law, is equal to K, Q1, Q2 over R squared, okay? K is considered Coulomb's constant. In AP, they have us use 9 times 10 to the 9, and that is newtons, meters squared over Coulomb squared. Those are the units for Coulomb's constant. K can also be written as 1 over 4 pi epsilon naught, okay? Those combined, and we'll show a little bit later in some different topics why this might be a little bit more beneficial to use it at times. Almost always, though, just using K is acceptable, okay? But K can also be written like that. It's the same value, right? And then this is the value of charge 1, the value of charge 2, and those should both be in coulombs. And then our distance between the objects, and we'll show examples of this, but this needs to be in meters. So those are the units for that to work out. And that works out because if we just look at the units, right, just looking at the units of this, force, which is measured in newtons, equals newtons meters squared over coulombs squared, multiplied by coulombs times coulombs, over, that's meters squared. So my meters squared cancel out, my coulombs squared cancel out, and we're left with newtons. So that gives us the units for Coulomb's constant, right? I write Newton's third law here, and this is important to remember. This is something that can be easy to forget. And the fact that if we have two objects that are charged, we'll give this a positive 4Q, and another object here which has a positive charge, but a positive 2Q. A common misconception is that the forces are not equal, right? But Newton's third law says that for every action there's an equal and opposite reaction, right? So these two forces are going to repel one another. And so because they're repelling, this is my action, we could call it an action-reaction pair, but this is the force on 4 due to 2, okay? And this is the force on 2 due to 4. And the thing is that those two values must be equal. They must have the same magnitude, right? And they're also in opposite directions. And a big thing with Newton's third law is that they have to act on different objects, okay? So this force here and this force here are going to be exactly the same size, right? If we had a charge here, negative 3Q, and a charge here of, again, positive 2Q, they're going to be attracting. This is the force on the 3 due to 2. This is the force on the 2 due to 3. For every action, there's an equal and opposite reaction. Those two forces are exactly the same size. They're acting in opposite directions, and they're acting on different objects, which all of that shows us Newton's third law. One of the last things that I want to talk about with Coulomb's law is that understanding that the force is a vector, okay, but we have to be careful with how we apply it here because the positive and negative maybe don't necessarily mean the direction that it's actually pointing in. On your equation sheet, you're actually going to see this as our equation. And it looks like this to show that this equation gives us the value. It doesn't necessarily tell us the direction that it's going to be acting on, right? Our absolute values gives us the magnitude, but not the direction, okay? And like what we just showed, if we have two positive charges here, a positive multiplied by a positive is a positive. This is squared, it's always going to be a positive, and this is a positive value, so it's going to give me a positive, right? The issue is that these are repelling forces. So this force here and this force here are both positive forces, even though how we think about direction, right? Even though this might be pointing in the positive direction and that's in the negative direction, these are both positive forces. Okay, so when you're looking at this, we have to use this equation to help us understand, okay, it's given us the magnitude, then we have to use our setup to help us understand the direction. An example of that is if I were to put a negative charge here, okay, what we see is that these two are going to attract. And so that then is going to give me a force here. Make it red to just differentiate. And it's also going to give me a force here. This force really is a negative value because a positive multiplied by a negative gives me a negative, right? But this is absolute value here, okay? So the magnitude is that value. Even though if we were to actually do the calculations, that's actually a negative force, right? But we see here a positive and a negative force are both pointing to the left. These forces were add together, right? The net force in this situation, the net force would be to the left if we were to add those two forces together because they're both acting to pull this positive charge in this direction, okay? Whereas if we were to look at the force between our negative charge and this positive charge, it's going to be a little bit smaller of a force because it's so much further away. That's that r squared, okay? This is also a negative force. Positive times a negative gives me a negative. But here we see that these two forces are actually canceling each other out, right? And my net force would be pointing to the right there. But it would be smaller than my positive force because my negative force is trying to pull it to the left. So even though this is a vector, and vectors typically, positive is typically to the right, negative is typically to the left, in electrostatics, we are just concerned about the magnitude, and then based on the physical setup, we have to understand if it's an attracting or repelling in terms of how those forces are actually acting on each charge.